Um, Thank you. As Ganesh mentioned, I'm in the IBM Systems organization, and I've been doing machine learning, deep learning, and HPC, as well as data analytics for quite some time. And our topic today will be Machine Learning and Deep Learning 101 Introduction. Our objectives are to understand how they differ between machine learning and deep learning, and how they're used generally in the context of analytics. We'll talk about the iterative nature of the workflow and some of the important components to be aware of as you're developing your AI solutions. We'll talk about the different types of algorithms and when machine learning might be more appropriate than deep learning or the other way around. And we'll talk about some life cases in terms of examples and outcomes, things that you look at when you're evaluating models. So traditionally, clients do data analytics with a number of tools that are more static than what AI brings to the table. So typical examples are spreadsheets where there's no governance, no collaboration, and fairly simple in terms of the work that gets done via spreadsheets. We also do business rules where rules are set and not very dynamic and more difficult to change as your business changes. Homegrown applications take those preset rules and are more flexible, but still very static. And then of course, there's many other applications like CRM and ERP applications that use analytics but are more towards business rules and business goals. What machine learning or AI in general bring to the table is some additional capabilities based on finding insights with your data. So in the 50s and 60s, the concept was already there and generally described as artificial intelligence. And the idea was using machines, systems, to do some of the insights from data that humans do. In terms of machine learning, it picked up in the 80s and the 90s, and that was more about using mathematics and systems to come up with insights. And deep learning recently, in the 2010s, in particular 2012, came up with some new algorithms that have a big dependency on how much data you have, but can get better accurate results than some of the machine learning techniques. So there was a renewed interest in artificial intelligence in the last decade. And so it's absolutely growing, I would say exploding, in terms of interest and capabilities that we can get from artificial intelligence in general. So the definition of machine learning is a system that provides the ability to automatically learn and improve from experience without being explicitly programmed. So what that means is instead of using the rules that we talked about earlier in the traditional analytics space, business rules, spreadsheet rules, and so on, you're now learning from your data and getting insights without the explicit programming. So you're basically helping your system find features, but in an automated and non-rules-based way. So what's the purpose of all of this? It's to go from data to actions. There's 4 stages in data analytics that we typically talk about. The first is descriptive. So based on your data, what has happened? The second is predictive, what will happen? Finally, it's prescriptive and cognitive. What should we do, and can we do that by learning dynamically? So you go from data to an action based on those insights. The idea is at each stage, depending on how much human input you're putting in, you're further along in this data insights. So the idea is to go from as much machine input and insights to as little human input and insights, and then just leverage that human input with subject matter expertise, for example, to make those final decisions based on the insights that you have, what actions to take. In general, the machine learning flow, and this applies to machine learning and deep learning, is you take your data, sample data, for example, could be credit card transactions, loan applications, MRI images, house data is the example we'll look at. Basically, any kind of data, you can put in a function and get a prediction from your data. So this is predicting an insight. And then based on that prediction, you have an outcome. So for credit card transactions, it could be fraudulent versus legitimate. For a loan application, it could be approve or reject. For a medical imaging system, you might determine whether a tumor is benign or malignant. If you're looking at home ownership data, you might have a prediction of what the house should be appraised for sale. So these apply to any industry pretty much at this point. Across all industries, you're going to find this kind of machine learning, deep learning flow when you have an AI system. Again, it's not a memorization or caching system in terms of business rules, but instead it can be represented by a mathematical function. So when we talk about machine learning and deep learning, we're basically talking about calculations, math calculations. And that's one of the reasons why there's so much interest in GPUs in this space, because you can do a lot of calculations very fast. So looking at the estimate of a house price, in the US, we look at how many square feet a house is, how many bedrooms, how many bathrooms, and this is a very simple example, is based on that, you could estimate a price. So in this case, your data is some samples where you've got features of square footage, bedroom and bathrooms, and you've got a label of a price. So with this combination of features, this is what we would predict the price. So this is what we call the labeled data set. When you have labeled data, meaning you know what the ground truth is, it's called supervised machine learning. If you don't have labeled data set, it's called unsupervised learning. And in this case, the objective is not to find a label, to predict the label, but to form clusters based on the data to look for patterns. So an example of that might be revenue, profit, number of online purchases, and number of store purchases, and predicting clusters of sales functions, for example. So data is a prereq to AI. This chart is a little bit busy, but hopefully if you're in the IT space, you recognize a lot of these data sources, basically. So you could be having real-time data processing and analytics. You could be having operational data where you would use databases and extract data from your databases, structured, unstructured. And then you would have exploration and archive data. So basically, lots of different sources of data, whether it's Spark, Oracle, Cassandra, MongoDB, Hadoop, data lakes. You basically have a data system where you've got information that you can integrate, that you can govern, that you can secure. And so this whole data piece of machine learning and deep learning AI systems is really a critical piece. Now, the types of data that you can look at is we looked at labeled versus unlabeled data that you'll use in supervised or unsupervised learning. But you also have structured and unstructured data and have data from all these different sources and different types of sources. So those could be transactional, system of record data. It could be other enterprise content. It could be sensors, instruments. We talked a little bit about MRI data. It could be data coming from spreadsheets. It could be geospatial data, social data like Twitter feeds, third-party data like weather data that from like the weather company. It could be data from chatbots, personal assistants, supply chain information. It could be financial information. It could be behavioral information. There's basically any type of data that you can come up with for your AI system. Once you have that data, you're going to be able to look into your business problems, define a problem that you want to solve with AI that is a good fit for an AI solution. Those fits are typically where you've got good automation potential, good subject matter expertise that can help you define what your AI system should be. Then you prepare the data, train your model, evaluate your model, fine-tune it, look for accuracy requirements, and deploy and monetize finally your model. So this is an iterative process. And what we'll do is talk about some of the key features of all these different steps in this session. So in terms of business understanding, that's always the first step when we do workshop with clients, is to make sure that everyone is on the same page in terms of knowledge of the problem. What are you trying to solve? Is it something that can be predicted, that could be, that you could advance your business case with a prediction? So the key here is to be able to articulate your use case. Again, I mentioned it applies to pretty much any industry that you may be in. So there are use cases that you can think of and that maybe others have already thought of to address your business challenges. Then you need to look, as we just talked about, to make sure that you've got supporting data and that that data is available to build these AI systems. You need to look at how much data you have and what type of system responses you need to your AI system. Do you need real-time inference? Do you need real-time predictions? Do you have enough infrastructure to read through the amount of data that you have? So there are a lot of questions in terms of implementation that tie back to business requirements of, have you saved the right data that you need? Are you getting your prediction results in a quick enough time for inference? Some of the common patterns of analytics business problems that we see and that you'll see tied back to what I talked about: planning, descriptive, predictive, and prescriptive functions of what you want to do with that data. Range from forecasting types of use cases to understanding historical events to predictions of future events, helping detect anomalies and segment your data, discovering new insights that you may not see upfront in your data, infusing natural language and understanding from that perspective of text and speech recognition, and then basically putting it all together with the systems that take all these insights and pull things together. So you can see with images, deep learning is where there's a nice fit, and natural language processing, of course, is the whole field of speech and text recognition. And there's a mix of supervised and unsupervised in most of these areas. So solving business problems with data and AI will utilize a combination of these analytics patterns. So you're applying AI systems, but you're also keeping your analytics infrastructure, in a sense, and systems to come up with updating and improving your business outcomes. One of the key things, again, in terms of preparation, before you can even start modeling is to make sure you understand your inputs and outputs, and learning how to map them to the applications that you're going to use these outputs in. So we talked a little bit about for example, banking transactions and fraud being the output. Is it a fraudulent transaction or not? And then feeding that into a fraud detection system. Same with audio and text transcriptions, and what applications are you going to be using those outputs in. So you're ready to start solving your business problem. The next step will be to prepare your data. So we talked already about finding your data, making sure that you have access to the data, which is where security and governance takes such an important role in the enterprise world. And with visualization, you're going to be able to get a first pass, a first sense of what the relationship is between the data that you've got access to. And that could be before even going into some of the deep learning and machine learning models. So you're going to use visualization to look for clusters and patterns, to understand your data distribution, to look for correlations. There are many, many open source packages on OpenPOWER that help you do these first pass visualization of your data. And it's a good starting point, because when you prepare your data for modeling, you do want balanced data, you do want clean data, so you might need to do some one-hot encoding, you might need to do some cleaning of blank fields or whatever it is. Understanding your data up front with visualization is a good first step. The second piece of this is going to be, in the case of structured data, and machine learning, is to do some feature engineering. So one of the things that we've noticed as we're working with clients is that many data scientists spend more time in this space than they actually do in the model building. And that seems to be a common theme across the entire industry. Feature engineering, data engineering, takes a lot of work and improves your accuracy downstream, and that's why it makes sense to spend so much time in this area. So there's feature engineering, that's basically defining the features based on existing features. So for example, if you recall the example of the house, the square footage and the number of rooms were features. And then you can define derived features based on that, which are functions of some of the other features that you might have. Feature selection is important, missing values, how to handle non-numeric types. And basically what you're trying to do is find the best representation for your model, to feed into your model. One special note on image data. This is a very popular and growing area where you're using unstructured data and you're using images to do AI. And those images, in a sense, you can think of as vectors and mathematical feature vectors. So in the case of a 256 by 256 pixel image, you've got 65,000 images, and each pixel is considered a feature in a feature vector. So you can see when you're doing models with images, you've got this highly computationally intensive workflow going on, because you've got so many features when you're working at the pixel level. One final piece of data preparation that goes into play is this test and train concept. So when you've got your data, what you want to do up front is remove a piece of data, typically 20%, but different data scientists use different rules of thumb, to set aside and not use either in the training or in the model building validation, so that when you are done training your model, you have a set of clean data that the model has never seen that you can use to evaluate your model. So that data is called the test data. You take it off the top or the bottom of your data or randomly as you wish, and make sure that that test data is saved for evaluation. With the remaining data, you again do an 80-20 split typically, where you use 80% of the data to train your data. That's, in a sense, going forward, using that information to adjust your model as you progress, and using the cross-validation data, that second piece of data, to test as you're moving along the model development. So you're going to train once, make some guesses, look at that validation data, see how far off you are from your guess. So that's your loss function. And that function is going to help you adjust your model so that you can predict again, and then validate again how far off you were, look at how far off you were in terms of loss function, update your model, and iterate that way. So that's the three types of data that you keep up with. And the reason for doing that is because you need to have a way to evaluate your model when you're done, and you also need to have a way to determine if you've underfit or overfit your model. And what that means is, in the case of underfitting, it's typically that you don't have enough information to get a more accurate model. And in the case of overfitting, you've used the training data too much, and now other random data will not get as good predictions as your training data, because you've, in a sense, somewhat memorized a little bit too much what prediction you should get, and it's not generalized enough for new data. So we talked a little bit about this loss function, and it's the goal of a model, and this is applicable to all models, is to minimize your true ground value, your actual value relative to your prediction, and make it as close as possible. So you'll start off this curve on the cost curve, and as you iterate, you'll get closer and closer to the minimum. And so you can see, as a function, and thinking about mathematics, finding a minimum of a function is a very well-known problem, and has many, many different algorithms to find the absolute minimum, localized minimum, and so on. So that's where the computational and the iterative nature of machine learning and deep learning come into play. It's to minimize that loss function. As I mentioned, we separated out supervised versus unsupervised learning early on, whether you've got ground truth and labeled data or unlabeled data. And there are different types of algorithms for these different types of learning. I'm going to go through a couple examples of these different types of learning, and then we'll spend more time on the deep learning piece, because that's the one that's really generating a lot of new interest in this field. So logistic regression, especially in the case of binary regression, is quite simple. The idea is, and this is unsupervised learning, the idea is, can you find a function that separates output categories, discrete output categories? So these are some of the very popular examples, and we've talked a few already about them. So medical imaging, looking for a specific thing in an image, yes or no. Credit card transactions, customer churn. Will a client likely leave leave as a customer or stay on as a customer. Email, normal or spam, language identification. These types of very simplistic logistic regression, and I would say many, many use cases, this works perfectly well and is sufficient for decisions in machine learning algorithms. Linear regression is the same idea, but in this case, your output is a continuous real space, real number space. So instead of being a 1 or a 0 in terms of outcome, it's a prediction along a range. And what you'll see is this applies better when you've got multiple dimensions and your outputs are not discrete necessarily. K-means is a similar kind of idea to find a clustering, but in this case, it's not a linear function. It's you start with centroids, the concept of a centroid, which is a starting point, and you're looking to cluster your input data points along those centroids and basically create groupings. So here, I don't know if you can see the color, but there's a blue, a red, and a green centroid, and you can see already where some groupings might occur around those centroids. So again, iterative, and you repeat until you converge into these clusters, and that helps you identify the patterns within your data. Very popular algorithm as well in machine learning. Deep learning relies on convolutional neural networks as an example. And the idea is to take data and process it through multiple layers where you're extracting information at every layer to get more and more information on your raw data. And so the easiest way to visualize this is to think of an image where you've got low-level features, which might be, for example, edges or angles or colors, and mid-level features as the next layer, where now you start to see potentially like a different, in this case, it's eyes or nose or other features in that image. And then finally, high-level features where you're extracting, basically reconstituting what you're learning from your low-level and mid-level features. And the idea, again, is you start with inputs. In this case, it's vectors of images, so pixels, very often three layers deep for color, and then pixel by pixel. And then you go through these different layers. And again, you're not telling the system what to look for. It is looking for these features or these patterns independently within the calculations that it's doing at every step, forwards and backwards, until you get a result, which is again a prediction or a probability. So there are different ways to look at this. That was the previous examples was very simple CNN. A recurrent neural network is also a very popular technique in deep learning, and that's typically used when there's a sense of time and space makes a difference. So you'll see this with time series, natural language processing, and video classification, so more with videos than images, for example. And there are different techniques and different styles to use basically a collection of CNNs in what we call a recurrent neural network, an RNN, to come up with a good model. The good news is that almost all these algorithms and techniques are built into these deep learning frameworks. So you don't have to code from scratch all the different layers, for example. These frameworks all understand what CNN is, what what a loss function is, depending on the loss function that you care about. So very popular to use frameworks, and these are all open source frameworks. And then there's a lot of add-ons beyond that to make things easier to use. I'll mention just a couple that are very popular. TensorFlow right now is still the leading framework. It was invented by Google. It's open source, and there's a lot of add-ons like Keras, for example, that use TensorFlow as a backend, where this is what you're using to develop your deep learning algorithms. So the idea is graphs where you're using tensors, which are arrays of numbers. Again, going back to the fact that this is just a function that you're developing. And the programming model is you feed the data to the network and it trains. Once it's trained, meaning it's gone through forward propagation and back propagation and adjusting biases and weights at every iteration. Once you're happy with it, it'll give you a forward propagation model inference, which you use to come up with a new result with new data. Most widely adopted and also one of the best documented frameworks. So very useful as you're getting started to understand all the deep learning concepts. The second framework that I'll mention is PyTorch, which has really come into its own in terms of popularity. It's coming out of Facebook, and that's what they're using for their research AI projects. It supports dynamic computations, and the very popular part of it, which is attractive to many people, is that it's based on Python with NumPy compatibility, and it supports multiple GPUs. Very intuitive, easy to use, and supports standard debugging tools. So it's a popular and I would say growing framework. All right, that covered some of the unsupervised learning. It covered deep learning, again, which is very popular with images or anything, any data that you can transform into images, such as audio data and satellite data, things like that. I wanted to spend a little bit of time on transfer learning because this applies to machine learning, deep learning, and specifically for deep learning. What you can do is start off with a pre-trained model and fine-tune it, as opposed to starting from scratch every time. So what do I mean by that? When you start from scratch, what you're doing is you're training all the parameters of your model by yourself, starting with a random starting point for your weights and biases. So you're going to iterate a lot to start to remove the bad values from the random starting point that you picked. When you fine tune, you're training many or most parameters by yourself, but your starting point is a model that has prior weights that has already done a fair amount of training up front on some of those low-level features, if you will. When you're doing feature extraction, you're training, you're fine-tuning, but you're starting at the very, very last classification layer. And that's typically when you have a model that is almost doing what you want it to do, and you just need to give it a little bit more information and give it some new classification layer to complete the job. So this is a function of your data set size and your data set similarity in terms of which technique you would use. You would use train from scratch if you've got very different data and large data set that you've got enough information that it can learn and learn quickly, even with a starting random point. So that's when you would train the entire model. When you've got a small data set, but you still have a lot of similarity, you're going to train some pieces of the model and then use some of preset training. And depending on how much similarity your data has, you're going to determine how much training layers you're going to leave alone and start at the end. And then finally, if you've got a small data set that's similar to other data sets that have been trained, you're going to want to freeze the convolution base and just focus on the classification, the final classification layers. Finally, one other technique that typically is separate from the machine learning techniques we just talked about, the deep learning with the transfer learning techniques that we talked about, called reinforcement learning. And I think of this more as a brute force learning with getting rewarded as you train and as you guess correctly. So this is maximizing long-term reward, and it's very popular in the gaming industry, simulators, robotics, stock prices, and that's called reinforcement learning, which is another set of algorithms. All right, so we've made it through our data prep. We've made it through our model development, picking the right algorithm. Now it's time to interpret our models. So I mentioned already the difference between machine learning and deep learning is with machine learning, you spend a lot of time developing features where you're basically telling your model up front what to start looking for. On deep learning, again, you're using these neural networks and you're not giving any additional feature information to the model. It's going to extract the features and classify on its own. What you want to do at this point is evaluate your model accuracy. And this is just an example with the vision models. Humans tend to have a 5% error in correctly identifying an image. Prior to 2011, using machine learning based tools, these systems were getting around 25–30% error, which made it not that attractive since it was not as good as the human eye. And starting in 2016, the models that have been developed and published are showing a 3% error or less based on these new deep learning algorithms. So now all of a sudden, implementing a vision model can be very attractive because you can get as much accuracy as a human and possibly free up some routine tasks or errors that arise from human fatigue or not enough resources to do not enough specialists, for example, to do the human component of image recognition. So that's why you're seeing a lot of interest. One of the base models that, for example, are used in a lot of transfer learning models is ImageNet. This is a set of data that is over 1 trillion images with many, many categories, and you'll hear ImageNet talked a lot about because it's used as the standard benchmark for evaluating how good a model is from a vision perspective. So as I mentioned, up in the 30% area, the first ImageNet model that was developed and published was AlexNet that showed a dramatic improvement. And then since then, those concepts and ideas have been applied every year to the point where in 2017, some of the models were down to the 2 to 3% range. So to keep in mind how a model works and why we look at accuracy, it's always good to go back to the business model. So if you had all the data in the world and all the information, you in fact wouldn't need a model because you would have 100% of your pattern, 100% of your answers. The idea of doing a random model is at any point in time, you're going to have, a random 50% chance of guessing what your prediction would be. So the idea is, can you come up with a better perspective of your population with a smaller sample of your data set? So this is why we're looking at model accuracy based on input that you're giving it. Is your model sufficiently accurate to predict for your whole population? So we're now at the point where we've trained a model, evaluated the model, and ready to consume it. That's typically called inference. And the function of the model is typically called deployed. So you're deploying a model for inference. The challenge here is it's very nice to have a very accurate model, but if you're not using it in a way that is beneficial, you're not getting any value from it. So some of the very typical examples are applying these inferences in a greater system. So an example might be in a call center where you're getting live information about your caller based on AI that's helping you make better decisions in terms of responses to your client call. Another example is putting an inference in a mobile app or putting it on a dashboard that you've customized. So there's a lot of ways to consume the model. And the idea here is that this is a very important piece of your end-to-end solution. This is an example in IBM that we have to demonstrate that, something called Visual Insights, and it's a vision model. And what we're doing is we're applying it to our supply chain of our clients, whether it's packaged goods, in this example, pharmaceuticals, automotive, any supply chain type of manufacturing or industry environment where you've got different points in which a visual inspection can improve your outcome. And these are typically called quality inspection systems. You can build a model that looks down and looks for defects. You can build a model that looks for packaging as you're going through the manufacturing line. You can look for label correctness. You can look for inventory placement, things like that. In all of these cases, we've got data. Some of it sometimes is near real time. Sometimes it's just fixed images or videos. You train the model and then you apply it to a dashboard and get information that you can then connect into, for example, MQTT systems where you've got, you send actions and functions to take as a result of your inspection. Another example that uses OpenPOWER is an AI appliance. So again, this idea of taking AI and turning it into something ready to use and productive. And in this case, one of our partners called Novi Systems built an AI system that takes sources, data from many different sources and applies analytics to this data fusion concept where it's taking all these different sources, developing fact tables so that now subject matter experts can poll for information and get decisions from that AI insight. And Novi Systems, if you look it up, recently did something for COVID-19, which was very interesting. And you can look up on the web their COVID-19 dashboard that is doing all of this on Power under the covers of looking at data from multiple sources and putting them together in terms of called data fusion to get information out. So we talked about all these different components. I just want to conclude with the fact that this doesn't happen in a vacuum. You do need an AI infrastructure to take you along your AI journey. We talked about data, we talked about training, we talked about inference and how all these pieces come together. In terms of data, we talked about starting with data and getting all the way to insights, so from edge to insights. And your data requirements will change as you go through this journey, whether it's from temporary landing solutions for your data and whether it's performance or capacity tiers in terms of throughput and performance requirements that are needed. I'll also mention here specifically archiving is a component that sometimes seems to be forgotten, but a lot of the data that you collect, you also need to keep. A lot of your models you need to keep. So there's a lot of systems management and data management that comes into play as well. And I'll also mention the importance of metadata and being able to find your data quickly, even before you get to modeling. And that's with tagging and indexing your data. So having all those tools come together in a data pipeline to go along with your modeling pipeline is very important. So in summary, machine learning, very computationally driven, but you need to start by understanding the problem to solve and determining whether you've got labeled or unlabeled data, which will drive whether you're using supervised or unsupervised learning techniques, determining whether you can use deep learning techniques as opposed to the more classical machine learning techniques. That'll depend on how much feature engineering you can invest in. It also somewhat depends on explainability and making sure that the algorithms that you're using can be explained and correctly evaluated. It's an iterative methodology. As you get more data, you update your models. As you update your models, you check for you validate them, and you check for accuracy, you check for how long they take to train, and you basically iterate on that process for the best end-to-end solution. You will get greater accuracy with deep learning, but again, there's pros and cons of going down that path. And then the true value, again, is when you have a model that you've built that you can inference. And then finally, I'd like to close with the fact that infrastructure matters. And that's something to pull everything together with your models. Hopefully, this was useful for you. If you're working with clients and they need some extra help, we're always here to help. Do workshops, co-creation labs, and training like what we just did here. So, thank you.
Clarisse, thank you for the wonderful, the fundamentals of AI, ML, DL frameworks and use cases. This is very good, actually. There are a lot of beginners also started joining, the webinar, and this is a kind of a special webinar we started for, some particular countries. And there are like a bunch of university, the undergrad and postgrad and researchers are part of this webinar. So I think definitely, there will be more requests coming in, and as we go along, if you have more time, probably you can spend, 30 minutes, 45 minutes, with these kind of, the new seeds, which we have been, creating and developing, in this region, especially Asia Pacific. Thanks again, Clarisse. And, interest of timing, I would like to move on, to the next session. Clarisse, you can answer, answer the questions, in the window, the Q&A window. There are a lot of questions, bunch of questions people are asking. And in the meantime, let me invite Professor Abhinandan, for his talk. Abhinandan, Professor Abhinandan is one of the professors in India. The college name is National Institute of Engineers. They are the one of the few in India who have got the IBM's the most powerful AI system called AC922, and he also did an international speech about the OpenPOWER edge computing and AI recently, and definitely his experiences will be very useful for this crowd. Professor Abhinandan, I welcome you to start your presentation.
Yeah, thank you, Ganeshan. Thanks for giving me an opportunity to share my experience. Especially OpenPOWER is actually helping us a lot. After we got IBM AC922, right? I'm doing a lot of work in that area, and it's really a beast. You won't believe few of the things which actually would take days to train with OpenPOWER. We are actually finding it within an hour. So we have a 2 GPU cards installed, and the training time has reduced a lot. So, and we are actually using it for semantic segmentation and all those things. But before that, I actually want to share our experiences, how the journey of OpenPOWER started. So let me share my screen now. Okay.
Yeah, it's visible.
It's visible, right? Yeah. Okay. So I am Abhinandan, and I'm an associate professor at NIE Mysore. Actually, I did my PhD from University of Göttingen, and after that, earlier I was actually working as a researcher in the area of cloud computing, and slowly I shifted it to machine learning and DL. So here in this session, I want to give my experiences, how the journey of OpenPOWER started with NIE, and how we are collaborating, and what are things that we are doing currently. So especially the agenda of this today's talk is on two things, important things. One is hackathon in a box, and then Edge AI. And this hackathon in a box is the relationship we started with the OpenPOWER Foundation, and especially with IBM and Ganeshan. So this actually was a crucial step in our journey, and we would say we can easily say this is the most fundamental work we started with OpenPOWER, and it's a cornerstone for our relationship. And then we will see how why we need to go and look into the Edge AI. So which is which is a combination of both edge computing and AI, and which is tomorrow's technology. So these are the two things I want to cover in this talk. Please feel free to ask questions. So let us go to hackathon in a box. So the first fundamental question is what and why we need hackathon. That is a fundamental question. See, if you see the companies, right? There are a lot of companies which actually come up with an hackathon, and you might have actually seen that you can some companies will advertise saying that okay, we are conducting hackathon on some of the technologies or some of the industries and all those things. So basically, let us understand what is an hackathon first. See, it is actually very simple, right? So the collaboration, the fundamental philosophy of an hackathon is collaboration. So and the collaboration is one of the one of the most important, and it is most natural instinct for any people for us, right? So whenever we get a problem, we actually go and talk with people we know, and then we come up with a solution, right? So the same thing when we apply it to an idea. So for example, if I want to build a software, what we do is we collaborate among our friends, and then we develop the software. And the same thing happens for technology also. Let us say that some companies wants to popularize this technology, what it will do is it will show it will organize a hackathon so that the people would actually collaborate on that idea or technology and come up with an usable software or prototype. So basically it is to show that, okay, using this technology or an idea, you actually can do a lot of good things. You can solve the real world problem. And not only that, the hackathon actually spurs the innovation. So when you collaborate and then you have come through you have actually already have an idea of the problems that you are going to solve, and you will actually use that as a basis to come up with a solution which is innovative in nature to solve the local problem. See, in Asia, right, we have a lot of local problems, and most of the time the local problem require local minds. And these hackathons, what happens is that the local minds will actually collaborate, and then they actually use this technology and come up with a solution. And this approach would help to build an ecosystem. So that's the reason companies or any organization, in order to push the technology, they use hackathon as a tool. And with the ecosystem, with a strong ecosystem, you get the much better product, mature product, which can be applied to a real world scenario. This is the crux of hackathon. So this is the reason we want to conduct the hackathon. So let us see, if I want to do the hackathon, what are the things that we have to do? First and the foremost step is planning and marketing. So why we need plan and marketing? See, all the collaboration would make sense when we have a motivated teams, right? See, in a team, if you don't have a good motivation, you will not, the solution what you create might not be a good one. So for that, what you have to do is you have to have announce the attractive prices. In our hackathon last year, we actually gave the winners iPad, and then you have to give the publicity of the event in the local newspaper and the social media nowadays, so that people would know, and people from across the country would actually join. And then once you have the good teams, if you have the good teams, then what you need? Money, right? So you need to have the right sponsors who actually could sponsor your hackathon, so that you can actually build the expertise. So for that sponsorship, you have to create and share the database of sponsors. You would know which companies you need to, or which organization you need to who are willing to fund you, sponsor your event. One of the key things are, if you want to actually, for example, if you actually want to push a technology, you need to look into what are the companies in your locality are using that technology. So go and approach those kind of companies. So saying that, okay, we are conducting the sponsorship, conducting event on such and such technology, and this is beneficial to you. So when you actually going and talking with them, you need to tell them what's in for them. So you need to tell that how your hackathon is bringing the value add to them. So this can be achieved by writing a funding proposal. You write a proposal saying that, okay, this is our strength and these are the things that we are going to achieve. And then you approach them. Possibly don't at least give them a time of a month. Otherwise, what happens is if you go and approach them near the event, like possibly a week, then they might not help you. So because they also have their budgets and all those things. So if you want to conduct the hackathon, plan it in advance. Possibly start, I would say, at least 2 or 3 months earlier. 3 would be the best, because to actually have the logistics, and then you have the sponsorship. So once you have the sponsorship, then a lot of things will become easy for you. The next is, once you on that day of the hackathon, you need to have big hall or conference hall in hostels or universities, I would say universities would be the ideal place. And then you actually, one of the motivation, not only price, food is also a motivation, right? So give them the ample food and especially try out with the local delicacies, and then you can actually have the sponsorship from the eateries also. So which we actually got it. And then you need to have the internet speed. You have to have the website for with online payment gateway, and then you need to have the dormitory for the non-local teams, because you should not conduct a hackathon only concentrating on the local population. You need to ask people. You need to talk with the people. Public. You have to do the publicity such a way that people across the country would actually come to that hackathon. This would actually give the visibility, and then you actually, the if you are conducting from a perspective of university, you are actually uh, you are actually you are actually bringing the young talents, right, bright talents. You are actually so that the talents which are scattered across come to a one platform, and it is a good time to collaborate, right? So you make good contacts, and then in future you can have a healthy collaboration. So that's the reason you need to take especially some care when you actually do the on the day of hackathon. And then one of the, not only that, see, on the day of hackathon, what happens is that you guys actually would be doing the collaborating and then working on your projects. At the same time, you need to organize the guest lectures, which can be from industry and academia on the theme of hackathon. So, for example, when we conducted, it was on the scaling AI applications. So what we did was we actually introduced, we actually had a guest lecture from IBM and then from some academia who those experts were actually were doing the research on the scalability, AI, especially on the AI scalability. And this gave a lot of insights to our participants and the audiences. So this would actually enhance the quality of your hackathon. And then the jury, the most important aspect of any hackathon is jury. So if you are an organizing or a host institute members, you should never be a part of jury. You can be an organizer, but don't be part of a jury, because it will reduce the bias. So in order to improve the credibility, go and talk with some industry and academia people and then bring them. And the whole part of hackathon in a box is to encourage the innovation. And I would actually talk with, I will show few of the most, one of the innovative projects which was finalized in our hackathon. One is the neural style images. So basically, what is neural style transfer? You actually manipulate the digital images to adopt the visual style of another image. For instance, these are the two images, right? One is Joker, which is very well known, and this one is a art. So the idea is, can we actually transfer the image of that the art to this Joker? This was this was the idea. So which is not a which is a common thing, because if you see some of the Facebook apps and all those things, they try to do that. So the idea is, can we do it through the machine learning? And one of our team actually did that. And see, this is what the output looked like when they transferred the image of the art to the Joker. So this is how, with that background art, when you actually impose on the Joker, this is how it would look. So it is not just a straight it is not a straight imposing. It is that basically what happens is that model would actually retrieve the style of that art piece and then incorporate into this image, so that you actually will have the illusion saying that, okay, the style that you have actually transferred, you created on one image, you transfer it to the other image. This is one of the project we had. And this one, the gender classification of silk form using deep learning. See, I think even in Bangladesh, this is a common problem. You actually, right? How do you get the commercial sales? You actually use that. You actually take the cocoons and you actually boil it, and then you actually make a commercial silk. See, the thing is, you cannot actually get the silk from all the cocoons. So you have to identify the genders. So how you do how do you do that classification? See, currently what happens is that is a manual. So you employ a labor set of laborers who would look into the cocoon, and based on the markings or based on the features which they know. For example, if you take the last these two images, right? The left one is a female one. You can see that there are two black marks. So based on that, you actually look into it. Okay, if it is female, you segregate. If it is male, you keep it. So this is how you actually do the gender classification manually. And one of the team actually used machine learning. Basically, they used the deep learning, and they perform the gender classification of on that the images of the couples. So recently, this project has been funded by the government, local government. Actually, they were impressed with the output, and now they have actually started funding this project. So now we are going live. So this is the impact of hackathon you have when you conduct this kind of hackathon. Nobody thought that you can actually uh, use deep learning to solve a local problem, because if you see looking into the cocoons, right, it is a tedious manual job. So with this, actually they could actually cut through that tedious cut through the manual one. And then most of the time you can actually use the images, you train it, and then most of the time that you can use the deep learning to segregate it. This is one of the this project actually has won the competition. And then these are the couple of projects. One is the object classification in 3D point cloud. So you identify the three-dimensional objects in the cloud, and then you cherry pick the advertisement based on the article you have read. These are the data set. These are the open data sets that you can use, and then you actually predict the probability of the loan transaction, whether the customer can pay off within 5 days or not, which we call the delinquency telecom model, which is actually used especially in the mobile financial services. And this one actually is very prevalent in Asia, especially in India, Bangladesh. This delinquency telecom model is prevalent. So these are the topics that these are the final teams, the final projects which was selected for the second round. And as I told, the gender classification has won the competition. So you could see how the hackathon, what we actually started as a hackathon, ended up being working as a product now, which has been funded. So this is the power of hackathon. So you don't know when the product will which idea will work. So this is what we have done as a part of hackathon. And this is one of the images on the hackathon day. So this is this where I will stop. If you have any questions, I can take it. Otherwise, I can move it the edge AI, and then we can actually go to
Yeah,
edge.
let's move on to edge, Abhi.
Yeah. Okay. So before going to edge, let us briefly look into cloud computing. I hope you guys know the cloud computing. Basically, what we do is we keep we have a set of the whole point is that we have a set of applications, we have a set of platform and infrastructures. We keep it in the data center, and whenever we require, we actually access to the data center. That we in a very informally we can we call it as a cloud. So these applications are one example of your application is Google Drive. So basically, I think almost of you, every one of you has a Google account, and you might have used the Google Drive, right? So you push your documents to the Google Drive, and then whenever you actually want to access, be it from the house, uh, house or from office, what you do, or from university, what you do is you will log into your Google account, and then you actually open drive.google.com and you download it. So the whole point is you will put the data once, and then you can access anywhere you want. So, and not only that, you can actually share that link to your friends or your friends, or you can actually use it for multiple purpose. So as long as you have the right permission and the right link, you can access it. This is the example of the cloud. So basically what happens is that your data, your applications, and all those things are stored in a data center. Whenever you want, you actually access it on demand. This is what it is. It's a very brief explanation of a cloud computing. And not only that, the content you can actually access from phones. It can be servers, it can be on desktop, as long as you actually know the as long as it is hosted on the cloud. And another important example, very common example, it is your Zoom, right? So whatever we are talking or we are conducting the webinar is running on the cloud. See, none of us are owning Zoom, right? So this application is running on the set of Zoom servers, and whatever I am presenting it, and you guys are actually viewing that content, is an example of your cloud. So the next question is, okay, this is the cloud, and what is edge? See, you can view the cloud as a centralized facility where you keep everything in a data center. But the problem is, each and every time you actually go into access, you have to go to that server, that data center, right? So as a result, the time you take to get the data increases. We call it as a latency. So that latency actually increases. If you are near to the data center, okay, you get it within a couple of microseconds. If you are far away, still you can get it in milliseconds. So the thing is that the perception what you get actually it's different, right? For instance, if you take a YouTube, right? So as we know, if you are in a fast connection, you would feel if there is no jitter, then you will get an impression saying that okay, the network is fast and you don't experience any network issues. Then it is seamless. Otherwise, what happens is most of the time, if the network is not good, you will experience the buffering, right? It will pause for a moment and then it will start. So this actually due to the latency, because you have to connect to the YouTube server and to the content. So instead, if we actually keep the content near to the user, then I need not go every time to the cloud. I can get the content locally, and then if the content is not there, I can get it from the cloud. So this is the idea of the edge. So you keep the content, be it application or platforms or infrastructure to the near to the user, so that the user will have the better performance. This concept is not a new one. Way back in networking, we had a similar concept called content distribution. The same thing, for example, if you are actually watching a cricket, right, the load is higher, and when you are streaming it, you actually you actually distribute your content in multiple locations, so that the people from one region would access the server in designated to that region, so that you reduce the load across the servers. So this is the idea. So the same idea, you bring it and call it as an edge. So earlier we were doing only for the networking, now we do it for the applications. So this is what we call it as an edge. Typically, this is how the edge looks like. Nowadays, with the advent of IoTs and then the cars, vehicles, where you have a capability to connect to internet, what we do is that we'll no longer consider the computer as the edge end devices. You have host of devices, and the edge can be your router, your base stations, and you have a micro data centers, and which would connect once again to the cloud. This is an example of an edge computing. The next question is, okay, I have the edge computing, and then how I am going to use the AI. And in the earlier session, you saw the fundamentals of AI, ML, AML, and DL. I will not go into that because Clarisse has done a wonderful job. So now the question is, as of today, how the AI is being worked on top of cloud computing. See, let us say that you have a Google, every one of us has a Gmail, right? So what happens is that most of the time when you open your Gmail, you get a recommendation saying that, okay, you can actually see the ads. How it does, how does the system knows that the most of the time if you check the ads, it is very near to your content, mail content. So basically what Google does is it will collect the data and then they build a machine learning model out of it and they push the recommendations. So that's what the personalized recommendation based on your personal browsing habits. The same thing if you have the Amazon, right? If you have an online e-commerce website, so most of the time what happens is that you log in and you get a set of recommendations. So these are the things that is centralized in nature. So you connect to the cloud and the data what you have will be actually sent to the centralized server, and then you have a model and it will be pushed across. This is what as of today we are doing. And with the advent of edge computing, how things are being changing. So the thing is that, okay, instead of sending or doing the model construction at the centralized server, why can't we do it by ourselves and then update the central server, right? So basically you can think that the same thing similar to our decentralized governments, right? You have a central government, especially in the in most of the countries, the same case. You have a central government and you have a region-wise government. So local issues are taken care by the region, the government, and the policies and which is actually across the policies or the policies which affect the across the country will be taken care by the national government. The same model you bring it here. As you know, the edge computing is very near to the users. You use the edge capability to build a local model and then you aggregate it and build a central model. And one example is your Google I think most of you have an Android app, right? Your messaging system, your Google keyboard in your Android app is an example of this approach. So we call it as federated learning, which is actually becoming very popular. So what it does is you take it, you take the input from the each one of us have a mobile devices, and whenever we actually write the keywords, we build the model, and the model is sent to the cloud, and then disaggregated. This is what the edge computing is doing with the AI. So the next is, okay, these are the edge computing is doing is affecting. So what are the advantages of edge AI? See, AI is necessary for us to unlock the potential of the data we are generating at the edge. We are generating the tremendous amount of data. So unless analyzing the data is a tedious task, right? So you cannot actually have the manual labor or manual programmer to do that. So what you have to do is you need to have the AI, and then to get the insights. So basically you perform the data analytics on top of it. And then what happens is that when you have an edge, it provides the novel application scenarios and richer data to AI algorithms. For example, surveillance, right? You have a CCTV surveillance and all those things. So these are the new paradigm application scenarios for the AI. And then helps in edge AI helps in AI democratization. Since the edge servers are very near to the people, right? And they are affordable. So you cannot run AI as a black box. You need to go and explain how it is actually impacting it. So edge is the first step which actually will helping AI democratization. And then you have actually a cost effective way, you reduce the cost, and then finally it is self-contained, right? So we look into the edge devices. I will show it in a couple of minutes. So which is actually, you can see that you can do model building and all those things on those kind of devices, which are affordable. Possibly for $100 you would get Jetson nanoboards. We will look into it. And this is, believe me, this is also very, these devices are very powerful. And it is actually better, sometimes, most of the time it is better than your laptops and desktops. So this is the hype cycle. As actually you see, the edge AI is at the innovation trigger space. And Gartner hype cycle is the one of the global standard which actually talks about the um, which will actually talk about the give the overview of the emerging technologies. And you can see, actually you see the edge AI, you can see that in another 5 to 10 years it will actually the edge AI will actually reach the plateau of productivity. And generally, just for a briefly, let me introduce you Gartner hype cycle, what it does. See, every technology, right? First, it will have the innovation trigger. We think that, okay, we actually come up with a new area, and then we think, okay, these are the things that these are the problems that the new innovation would solve, which we call it the peak of inflated expectations. So basically, we will think that, okay, this technology would cure all the problems, will solve all the problems. After a couple of years, we will actually use it thoroughly, and then we will understand, okay, this is a technology which cannot solve these kind of problems, and we call it a trough of disillusionment. And then finally we assume, okay, we'll know, okay, these are the this technology will solve only this subset of problem, and then this is our scope of enlightenment. And once we are in the enlightenment position, we move into the productivity. So you can see in another decade, within a decade, the edge AI would actually be more productive. So this is what happened in 2 years back, and still it is valid. So these are the edge use cases where you actually use smart cameras to recognize the people who have entered. Basically, you can use it for security system. And then generally now we have a face recognition and object recognition on your phones, right? And then on the smart cars, you can self-driving cars, you can use it. And then you can use it for the baby monitoring, drones and robots. And drones has opened up tremendous opportunity in edge AI. So these are the edge devices I was talking about. This is a Jetson nanoboard, and this is a Google Edge TPU. TPU stands for Tensor Processing Unit. And believe me, these devices are actually very cheap. Within $100 you can get these devices, and then you have around 100 cores in Jetson nanoboards, and you can do a lot of machine. You can actually deploy a lot of good sophisticated models on those nanoboards. And these are our edge AI training architectures. The training can be done either centralized. Basically, you send the data to the centralized cloud, and then the cloud will build model. And a decentralized is you actually like federated. It is not federated is not a decentralized. Okay. The thing is that what you can do is that each edge device will build a model of its own, and then you actually coordinate among themselves. Then this is a decentralized, and then the hybrid one. So one example would be your federated learning. You make a local model, and then the local model is passed to the sent to the centralized controller, and the centralized controller would actually build a model and then aggregate, and it will push back. So basically, you actually have the both centralized and decentralized. This is what the hybrid model will look like. And then these are the edge KPIs we have. What is the training loss? how well the trained model fits the training data. So generally, when we do the training, as earlier session you have seen, we do the training, and when we do the training and the cross validation, two important things. So when we do the training, what we do is we generate the model, and then we fill the data, and then see what is the error we are getting, and then we keep on increasing to improve the accuracy. So the loss of training is one of the KPI, and then important important KPI is convergence, which you will not find in the centralized AI model, because as you know, in a distributed system, right? In a distributed system, each node has a capability of taking decision on its own. So it is similar to your democracy, right? So basically, at the end of the day, each one of us vote in a different parties, or different parties, and then you actually come up with a consensus to find a acceptable candidate. There are some cases where you will not. I might have voted X, but Y has come. That does not mean that I agree with Y, right? So this is how it is. So you can think that democracy as one example of a distributed system where you actually converge. So the decisions you actually taken when you build a model, how you actually build the convergence talks about how fast, or first the important issue is, are we coming with a concept, right? Sometimes which is pretty common in Asian countries, of about the hung parliament. So that's not a convergence, right? None of us has actually agreed. So when we talk about convergence, it is most of us has agreed. So this is what the idea is. So here in the convergence is an important step in an edge AI, because all your edge devices are capable of running the whole model, right? Building the model, and then you need to have the global view. So this is achieved through the convergence. So you build a consensus, and if I am building the consensus, coming to a consensus, then how fast I am achieving it. So that is the KPIs, and KPIs are nothing but key performance indicators. And then privacy, which is very much common, which is very much stricter in country in European Union, where and you have the communication cost. So for example, when you actually do the edge AI, right? So you include the network transfer also. So your network bandwidth plays an important role. For example, if you are actually true and fro, if you are sending a lot of network data, that will choke the network, right? And then it might impact your training. And then the latency, how fast I am actually inferring it, and then the energy efficiency. Because at the end of the day, you are using lot more devices, which would affect your power, right? So you need to, and then these algorithms, most of the artificial intelligence or ML algorithms are resource hungry, so which would require a lot of energy. So you need to reduce the energy efficiency, improve the energy efficiency. So these are the common edge interference model, as I told. So you have a edge. One is a very simple one. You actually use the edge base. You use directly edge server, where you have deployed your model, and then make an inference where you deploy it on the edge. And then device-based model is that you actually deploy the model, and then you actually do the training on the device. And then you have a edge device mode. You you build the partial models among the both by edge and the device, and finally you actually have, as the your partial model is split into the edge and the cloud. So basically, if you want to do the inference, you need to go and contact the cloud data center also. So your half of the model is deployed on the edge, and your other half is on your edge, and then you have to make the inference. So these are the four inference models what we have in the edge AI. So this is and this is our OpenPOWER AI Virtual University. Please do actually subscribe this one into this YouTube channel, where you can get the regular updates on the OpenPOWER and the innovation that is happening on the edge. So it is one of the most valuable YouTube channel. You can see it on AI, especially on OpenPOWER. Any questions?
Professor Abhi, thank you for your wonderful insights on AI, Edge AI, as well as the hackathon, which you delivered last year, as part of the OpenPOWER hackathon plans. And also, thank you for sharing, some of the details of, the edge computing and the features of edge and all the stuff. Thank you. And audience, any questions for Professor Abhi as well as Clarisse? So here, I know interest of timing, so here we planned for 1 hour, 30 minutes now exceeded, but we can still have 3 to 5 minutes, for question and answers. There are a lot of questions already answered by Clarisse from IBM, my colleague. And, there are still some questions, related to edge on the chat window, Professor. Maybe I can read out a few questions, as part of that. So there is a professor, I think Gopalakrishnan asking, so in edge, they will have secondary server at the node rather than the primary server, primary IoT server.
Actually, it is basically, it depends on your requirement. So
okay.
There is no standard answer saying that, okay, you need to have single or you have a secondary server. Generally, what we do is, you can see two things here. One is the Cisco came up with fog computing. So in the fog, what we do is, which is nothing but a primary IoT server, actually. And then we have a fog, we have a secondary called as an edge, and then we have a cloud. So if you are going from the perspective, if you are checking from the perspective of IoT, you can actually, one server edge is enough, but you can actually have the IoT, your primary IoT server can act as the edge itself. But it once again, it depends on your requirements. So if you go and check Cisco, right, they would call it as an fog, which is very near to the device. And the server, which is actually in between the device and the cloud, they call it as an edge. So it depends.
Thank you, Professor. And any other questions, audience? So there are a lot of questions related to ML and DL, already answered by Clarisse, my colleague. So let's move on. Okay, I think, interest of timing, and, we already exceeded some more time, additional time, we got, let's actually move towards, the end here. And once again, I would like to thank Clarisse, as well as, Professor Abhi for their wonderful, presentations today. And thanks to, all the participants who actively participated in the webinar. And looking forward to meet you all on June 26th. We have a special webinar related to enterprise and OpenShift, cloud, Kubernetes, and that too going to be shared by the enterprise experts. And one from IBM and one from our enterprise company called, the banking industry, Citibank. So please, do join us, on 26th webinar. You will all get the link to register. And thank you again for your time today. I'm closing the webinar now. Thank you.
Yeah, thank you.